Yeah, I just use T average.
So we are not going to spend that much time on fast transistor logic because this is hardly used. So we are going to, but later we'll use for a different purpose. So
Why it is hardly used?
we will explain because there are some drawbacks in terms of signal strength. So everything we have discussed, all the logic families we have discussed up to here, all the different circuit styles, all of these techniques have one common thing. Yes.
I have a couple of quick questions about the test next week, or like stuff leading up to the test.
Yeah.
So can we expect, we haven't gotten back our quiz 2 and 3 yet. Can we expect to get back like 2, 3, and 4 on Thursday so we can study?
That's
like,
what actually I told the TA to upload everything by tomorrow.
Okay, and then that also goes like, because the 2, 3 solutions are on it, then those will be
All
on
the solutions, actually, I'm meeting with him later today again. We had a conversation today. There will be also 2 practice homework on lecture 3 and lecture 4 with solution uploaded by tomorrow. So, and this Thursday, we are going to discuss problems. So it will be purely a problem solution class. The problems you will see in the exam.
But we have midterm on 22nd, right? So lecture 5 will not come?
Lecture 5, whatever we cover today, use it there. So in all of these logic style, there is one common thing except these two, that input signals are always applied to the gate terminal. Input signals in all these ratio or whatever we talked about, you just think about it. Input signals are always applied to the gate terminal of the transistor to turn on and off the transistor, the device. And output signals, binary 1 or binary 0, output signals are always taken from the drain terminal. So in any conventional logic circuit, drain terminal is the output terminal, gate terminal is the input terminal. So that is the convention, but in fast transistor logic, any of the 3 terminals, gate, source and the drain, can be used as input or output. That's the difference. Now let's look at this one example. So there are some advantages in actually any logic circuit can be implemented with significantly lower number of transistors. As a consequence of lower number of transistors, it will have lower capacitive load and it will consume less power. But in terms of signal integrity, signal robustness point of view, it has a serious problem, and also it has few other disadvantages. We will explain it quickly why we don't use it that much. So let us look at this fast transistor logic with an example. A 2-input AND gate, here is the truth table. For an AND gate, 0, 0 output is 0, 0, 1 output is 0, 1, 1 only output should be 1. Now, let us forget about this lightly shaded transistor. Theoretically, we can implement an AND operation with only a single transistor. It is so for a 2-input AND gate, we have 2 inputs A and B. How about we assign one of the two inputs at the gate, another one in one of the gate source, drain source terminal, and the other one we use it as the output. So now let's see. When B is 1 for an NMOS transistor, B is 1, for these two cases, the transistor is on. The value of A will set the value of output, right? When B is 1 in both of these cases, if A is 0, output will be 0. If A is 1, output will be 1. So if B is 1, this transistor is on. A is connected, short circuited because it's on with the output. So output will get whatever value you will apply at A. So it said it when B is 0, it is disconnected. That is a problem. We'll discuss why. But at least in these two cases, when B is 1, input A will set the value of output. So it is satisfying the AND operation. Except one situation, when B is 0, this transistor is on. This output, we don't have this transistor yet. This output node is floating. Floating means it doesn't have a connection to any source terminal supply. So it is floating node. When you have a floating node situation, you have no control on that circuit at that node's voltage. How do you know that it is 1 or 0? So the floating node situation will create an uncertainty whether, let's say, when B is 0, irrespective of what is A, output should be 0. But if the node is floating, if it has some noise injection, voltage will be raised above 0. Since the node is floating, there is no way to discharge that noise to bring that voltage to 0. Or if from previous operation, if this node voltage, output node voltage is holding a charge equal to 1, when you apply 0, disconnect it from A, so there is no way to discharge that previous one. So in floating state, it may hold anything from 0 to 1, because there is no way to set the value when it is electrically disconnected or floating. So avoid that, but ideally, somehow if you have way to discharge it, when B equal to 0, output should be 0, then you could implement the whole AND gate just a single transistor. But to avoid that floating node situation, we added a parallel transistor to this output node. That parallel transistor also it is getting an input of B bar. When B is 0, B bar is 1, this transistor is on, so output is connected. This side is permanently connected to ground, so output is connected to ground, so this node will be discharged, so I am taking care of this combination of input. When B is 0, A is 0, output will be 0. So to avoid the floating node situation. However, so now to implement this whole AND gate, how many transistors we need? 1, 2, and 2 for B invert. So 4 transistors, we can implement this AND gate. But in a traditional CMOS, we do not get AND gate directly. We implement NAND gate, 2 input, 4 transistor, plus an inverter, 6 transistor. So here we are implementing with 4 transistor, but in conventional CMOS, we are implementing it using 4 transistor in pass transistor. So it's a savings, but there are some problems. Problem number 1, in pass transistor logic, there is a thing called threshold voltage drop. So let us go back to this truth table. When B is 1, A will set the value of the output. When B is 1, this is on. If A is 0, and MOS is very good at passing 0. So this 0 will be passed to the output, and the output will be fully discharged, so I will get a perfect 0 here. But when B is 1 and A is 1, NMOS is not good at pulling up. So this output node will be pulled up to VDD minus 1 threshold voltage, even if A is 1, because transistor and most transistor will experience a 1 threshold voltage drop. So the output F, which you are expecting a 1, it will be a distorted 1, and it will be distorted or reduced by 1 threshold voltage of the NMOS transistor. That is called the threshold voltage drop of NMOS transistor. So the first disadvantage is, if you are applying a VDD A equal to 2.5 volt, which is perfect 1, should be equal to 2.5 volt, at the output node, let's say my output is B, inputs are A and C, at output node I will be getting 2.5 volt minus the threshold voltage of the NMOS transistor. So the output will be always distorted if I am passing a 1 NMOS transistor. If I am passing a 0, then B will get perfect 0. Now you can say, well, if A is not good at passing 1, why don't we use a PMOS? Then you will have the same issue when passing 0. It cannot bring it all the way down to 0. It will always stop at threshold voltage of the PMOS. So whether you use NMOS pass transistor, so since we are passing the signal from one side to the other to set the value, we are connecting input to the output. So we are setting the output not by connecting it ground or VDD, by connecting it one of the input, by passing input to the output. That's why it's called pass transistor logic. But while passing, either we get a distorted 1 in case of NMOS, or we get a distorted 0 in case of PMOS. As a consequence, let's say this pass transistor logic is driving another logic circuit. So this logic, let's say inverter, and a simple example, to turn it on, it needs strong 1 and a strong 0. If the signal that you are passing is weak already, so this transistor will not be turned on at full strength. So its slow, low to high to low transition will be either slow, further delay, or it will not have full voltage swing because the input itself will be distorted. So that is the number one disadvantage, the threshold voltage loss or drop as you are passing signal through transistor. So that leads to another bigger disadvantage. When you have a complex logic circuit, let's say theoretically, if you have more than one pass transistor connected one by one, what will happen? Let's say 2 pass NMOS transistor connected. If you are passing a 1 from here to here, first M1 will impose 1 threshold voltage drop, then M2 will impose another threshold voltage drop. After 2 or 3, your voltage will be in the undefined region, and this logic circuit will not get any meaningful signal. So cascading of multiple pass transistor logic is not possible because of the threshold voltage drop in each of the pass transistor logic. So, and in this case, in this simple design, since it's only 2 input problem, only 3 possible alternatives, we could see that in this input combination, when B is 0, it is disconnected, we will have a floating node situation. But if you are to implement even a 4 input problem for 16 combination, you have to check every combination. For every combination, the entire circuit, is there anywhere in the circuit a floating node appears. If a floating node appears, then it's not a static circuit. Only in dynamic circuit a floating node can appear. We'll talk about it later. So pass transistor logic, number one problem is, if you do not design the circuit carefully, for some input combination there will be a floating node situation. Then you have to have an alternative path to take care of the floating node situation. Number 2 disadvantage is threshold voltage loss as it passes through the transistor. NMOS will have a distorted 1, PMOS will have a distorted 0 because they are not good pull-up device. NMOS or PMOS is not a pull-up device. and cascading of multiple transistors is not possible. So, this is the summary list of disadvantages of fast transistor logic, why we do not use it. Reduced voltage swing due to the threshold voltage drop, which is explained. The other one is the body effect, that is a serious reliability problem. As we explained, in a MOSFET transistor, we connect gate and the body terminal, so source and the body terminal together, tie them up. Why? To make sure that PN junction, this is source, this is body, right? We always tie the source and body terminal together to the ground in case of PMOS and MOS to the VDD in case of PMOS. Why? We want to make sure that this terminal, this PN junction is unbiased, so zero bias, so that no current goes downward. But in a fast transistor logic, source is actively participating in signal transition. It is completely separated from the body. Sometimes, depending on what signal you are passing, 1 or 0, source will be 1 VDD above the body or 1 VDD below the body, depending on. So, there is a chance that this junction can get forward biased and short, depending on the polarity of the signal you are applying at the source with respect to the body. If that PN junction accidentally becomes forward biased, the current that should go from source to drain will move this direction, so the device will cease to exist or operate. If anything goes from source to the body, there's a drain, there's a leakage, so we are not going to be able to utilize that current to change the binary output at the drain, right? So that is called body effect. Across the body, a positive or negative bias voltage may appear that may flip the bias situation in this source body junction, may inadvertently shorten the source with the body. So that is called body effect. That is another problem. Floating output error, we just explained, for certain input combination, if we do not carefully design the circuit, there will be floating node situation at the output. Another problem is called short circuit error. If you, for a complex logic circuit, you will see that two different input will become short circuited through the output nodes. We will go through an example. Then cascading problem, we already explained. More than one NMOS pass transistor, if you connect one after another, and if you are passing one, every time it's crossing through an NMOS, it will experience a threshold voltage loss. So these are the 5 major problems of pass transistor logic, and that is the answer to your question, why we do not use this pass transistor logic. So now let us look at the short circuit problem. Another big disadvantage is in CMOS, we know we have to follow series parallel technique to implement any CMOS pull down and pull up network. There is a defined technique. Pass transistor logic, there is no defined technique. It's purely trial and error. It's purely trial. You have to try different permutation and combination of transistor circuits to make sure that there is no floating node error, to make sure that there is no short circuit error. These two must be avoided. Otherwise, the circuit will not act like a logic circuit. So now let's look at a simple example of F equal to AB plus B prime C. Now, if we follow this technique here, an AND operation, an AND gate can be implemented by these two transistors, and it will not have floating node situation because this B bar and MOS will take care of this combination. So if we just follow blindly that approach, what will happen? The first term AB in OR operation with B prime C, so they are in parallel. So AB first term I can implement this way. A going to first transistor as an input, A bar going to the second transistor as an input, B and 0 is connected to the output. So these two transistors together successfully implements first term AB. Similarly, for the second n term, we can take another pair of transistor operated by C and C bar. B bar can be the input here. So just independently these two transistors will implement B bar C, and now if we connect them together, combine them, that becomes like combined output. Theoretically, it should be okay. But the problem is, this is a three variable problem, A, B, C. In some combination, C will be 1, A will be 1. A and C, 1 means this transistor is on, it is connecting B bar to the output. When A is on, B will be connected to the output. So output F is equal to B and B bar. It is logically incorrect because I am connecting, this is F, to this node I am sending B bar, to this node I am sending B. F will be confused. We will get an erroneous value because logically it cannot be at the same time B or B bar. So logically this circuit is incorrect. That is called short circuit problem. We are short circuiting an input signal with its own invert through output. So logically it is incorrect. It cannot happen, right? So this circuit is, that means, yes.
So what happens when the two input, let's say, not in this circuit,
In any circuit, if
what happens?
for any, then that circuit is wrong. This
Yeah,
is
yeah,
no
this
longer
is
a
wrong.
logic circuit.
But what happens in the real world if 0 and 1 is coming to the
Then
output?
the circuit will malfunction. The circuit will malfunction. It's like if two of the wheels are rolling in this direction and two of the wheels rolling in this direction equal speed, the car will stop there, right?
Yeah.
Or it will break down. So if in any logic circuit, whether pass transistor based or CMOS based, if you run into a situation where for a certain input combination there is a short circuit appearing between a signal and its invert, that means you have done something wrong while designing the circuit.
So it will create a short circuit?
Yeah,
It's
the
creating, it's
circuit will
creating.
not function as a logic circuit. Any random transistor, resistor, capacitor you can correct any way you want, but the question is whether that's a functional circuit or not. Here, every circuit we are designing, it has to implement a certain logic function. And if there is a short circuit between a signal and its invert, then it is no longer a logic circuit. So, why this error? So how to avoid this error? We have to carefully assign the C's, A's and B's to appropriate terminals through trial and error again and again to make sure that there is no short circuit. Now I can assign C here, A here, B here, right? So now as you can see, we have an alternate implementation of the same circuit. So alternate implementation of the same circuit. Here what I have done, in this expression, B and B bar, both of them are there, right? F equal to A B bar. So I am using B and B bar as the two inputs for the two transistors. I am using A and C as the other inputs. So now as you can see, if B is 1, this transistor will be on. A will set the value of the output. If B is 0, this transistor will be on. C will set the value of the output. Now if you look at the expression itself, if B is 1, that means B bar is 0. If B bar is 0, that B prime C term will not contribute to your output because that term will become 0. So if B is 1, only A will set the value of the output. If A is 0, output is 0. If A is 1, output is 1, right? Again, when B is 0, that means B bar is 1. The term AB will become obsolete because B is 0, so term AB is 0. B prime is 1, So if C is 1, the output will be 1. If C is 0, output will be 0. So this circuit with two transistors using B and B bar as their respective input, A and C as the other side of input, it is correctly implementing the logic function. It doesn't have a floating node situation. It doesn't have a short circuit situation. And I can implement it on the 4 transistor. 1, 2, 2 for the inverter. Here I needed 1, 2, 3, 4, 2 for this, 2 for this, 2 for this, 6 for 3 inverter, 4, 10 transistor. Still it has a short circuit problem. By trial and error, I'm showing you the final product. In between, I tried different other options. So the final product is 4 transistor, no floating node, no short circuit. Now, I can simplify it further by reducing the transistor. How? A signal B bar going to NMOS is exactly equivalent to B directly going to a PMOS, right? So when B is 1 going to both transistor, NMOS will be on, A will set the value of output. When B is 0, this PMOS will be on, C will set the value of the output. No floating nodes, no short circuit, and I implemented this whole complex function with only 2 transistors.
Wouldn't you still have a floating node because none of those inputs is actually connected to ground?
No, because input should not be, we are assuming that input is supplied by either some source or some other stable logic circuit.
Okay.
That logic circuit, wherever the signal is coming from, will take care of those. So, whenever we apply the input, we don't have to worry about floating node situation. So this complex logic function, by trial and error, I'm showing you only 3 trials here. I came down from 10 transistor, still an incorrect circuit, to a 2 transistor implementation. So that's why if I give you any simple function to implement in pass transistor logic, very rarely you will have the correct circuit in the first trial. You have to implement multiple different versions and check every possible path, every possible input combination. You have to actually draw the truth table and all possible input combination and make sure that there is no floating node for any combination, there is no floating node for any short circuit combination. So that's why if I compare with this one to this one, it looks very lucrative in implementation because it can implement any complex logic circuit with bare minimum number of transistors, but it has lots of disadvantages in terms of signal integrity and performance. That's why it is hardly used. So there are some techniques people use, level restoration techniques to restore pass transistor logic. Let's say you are passing A1 from A to node X. It is an NMOS transistor, so it will have a distorted 1. So I can engage some level restoration technique. This is one of the noise suppression technique used universally in microelectronic circuit. A level restoration technique can be implemented to restore the signal back to full strength 1. But that is the expense of all these additional circuitry connections, right? So if you are talking about a very complex large circuit, probably it's worth. But if it is just a single NMOS transistor passing, probably it is not worth engaging all these complex circuitry and additional connections to restore this node. But what I'm showing is that there are ways to restore distorted output signal in pass transistor logic. So its advantage is it will give you undistorted full swing, no static power, and disadvantage is we are adding restoration capacitance, additional inverter, additional transistor, all the source connections. So this will basically add to physical resource as well as power resource, as well as it will delay the circuit because that whole circuit needs certain time to restore the signal. So at the expense of all types of resources, performance and physical resource, we can restore it, but it is in majority of the normal logic operation, it is not worth going that route. That's again validates why CMOS has become the dominant selection for any logic design. So these are some other alternative ways to make the pass transistor logic robust. One of them, they're saying that theoretically it is possible to design zero threshold voltage transistor. So what is the benefit of zero threshold voltage? What is threshold voltage? Up to threshold voltage, we don't have a channel. Lower the threshold voltage, the transistor will be on. Earlier, we will have a stronger channel. If I can make zero threshold voltage transistor or very low threshold voltage transistor, that means as I am passing the signal through the transistor, it will experience no drop if threshold voltage is zero, very low drop if the threshold voltage is very low. So if we can make this pass transistor zero or extremely low threshold voltage, then as I am passing signal through them, it will experience very minimum or ideally zero distortion if the transistor itself can be designed with zero or low threshold voltage. Then again, then you have to, but making zero threshold voltage or low threshold voltage gives rise to some other complications, some other leakage. Particularly, subthreshold leakage is exponentially dependent on threshold voltage, so we cannot take that risk. So, this is just, but again, as I said, it will increase the leakage significantly if you lower the threshold voltage. I'm just showing, you don't have to worry about, just go through this slide. There are techniques available. So now, later when we are going to use sequential logic circuit, not the combinational logic circuit, you will see that there are some use of pass transistor device. There is some use of pass transistor device where in some special circumstances we have to pass signal through transistor, input signal through transistor like this for the transistor logic, and we cannot tolerate threshold voltage drop. So there is a remedy for that. That remedy is called transmission gate. This one is widely used. It's a special implementation of pass transistor logic. It's called transmission gate. Transmission gate is not a different device. It's actually parallel connection of two transistors. An NMOS transistor connected parallelly end to end with a PMOS transistor. That combined device is known as pass transistor transmission gate. This is the symbol of pass transmission gate. This symbol means that inside this device there is an NMOS transistor connected in parallel to a PMOS transistor. So this transmission gate will have two gate terminals, one coming from NMOS, one coming from PMOS, and they must be operated with opposite signal. If I operate it with C, this has to be C bar. If I operate it with C bar, this has to be C. Why? Because they are opposite type of transistor. So a transmission gate can be a transmission gate. So, right? A transmission gate can be operated by like C bar C, or you can do the other way. C or C bar. So now, if C equal to 1, this NMOS will be on. C equal to 1 means C bar equal to 0. So this PMOS always will be on. So this transmission gate, the way here it is connected, this transmission gate will be on. Both transistors will be on when C is 1. So it's a positive transmission gate. It is on, completely on. It has two possible paths for the signal to flow. Why we need two paths? I will explain it. But as you can see, if C is 1, this NMOS is on because 1 will turn it on. C1 means C bar is 0, so this PMOS will be also on. If I flip the connection, if I make it C bar and C, this transmission gate will be on for 0. Now, what is the advantage of having two parallel paths, one through NMOS, one through PMOS in a transmission gate? And how it avoids the threshold voltage loss and the cascading problem and the reduced voltage swing problem of regular pass transistor logic. How it avoids these two disadvantages. Let's talk about it. Let's say you are passing a 1 from A to B. You have to turn on the transmission gate. Apply C1, it will be on, it will be on. So 1 will be passed very quickly from A to B initially. Why? You have two paths on. So this node B will be charged from A through here and through. So parallel path will be charging. So the charging rate will be much faster. At one point, NMOS is not good at passing 1, it will be turned off. But there is an alternative path that will take it all the way to VDD. So initially, from 0 up to VDD minus VTM, threshold voltage of the NMOS, the charging will be very fast, super fast, because it will be done through both NMOS and PMOS parallel path. And from here to next, this is small portion, VDD, NMOS will be off, but PMOS is still on. PMOS is good at passing 0, it's passing 1, so it will take it all the way to VDD. So I will not have a distorted signal. I will not have any threshold voltage drop across it. It will be all the way to VDD. So I can connect another transmission gate without fearing that there will be a threshold voltage drop. So the transmission gate avoids the threshold voltage drop and cascading problem of pass transistor logic, but it's still you have to be careful about floating node short circuit problem. So that is the transmission gate. You can turn it on with a positive signal, or you can turn it on with a negative signal, depending on how you are assigning C and C bar. So transmission gate you can basically utilize as a pass, or in later we'll see that it can be used as a switch. The only disadvantage is area-wise, a single transistor-based switch will be almost 2 to 3 times smaller, because a transmission gate requires an NMOS plus a PMOS. PMOS is 2 to 3 times larger than NMOS. So together, that transmission gate is at least 3 times larger than a single NMOS transistor. 2 times larger than a single PMOS transistor. So it will consume more area. More area, more transistor means more parasitics, more power consumption. So that's all. So later we will see some use of transmission gate, but at this point spend some time on the slides, but don't expect any actual logic design on pass transistor logic. So today we are going to introduce dynamic logic. This one will be very easy lecture because here the design you already know. So these are the things we are going to discuss here. So first, let us look at the general properties and characteristics of dynamic logic. So we have 2 types of logics. One is static logic, one is dynamic. Static logic is called static because its binary value is achieved by having a connection to ground or a connection to VDD. During the steady state condition, the output node in a static circuit will never become floating. It will always have a connection either to ground or to supply. By the virtue of that steady state connection, it gives us a binary 0 or binary 1. But in dynamic circuit, the output binary value in certain situation will be held by the output capacitor CL, and it will not have a connection to supply or ground. It will be holding that binary value 1 or 0 as a charge stored across this capacitor without aided by the VDD or ground. It will be holding it in floating state, disconnected from supply and ground altogether. So in dynamic circuit, ability to hold the binary value at the output depends on the charge storage of that output capacitance. That's why it is called charge storage based logic circuit. So its operation depends on charge storage properties of the logic circuit or the output node of the MOSFET, and depends on how much charge that output node capacitance is storing. It will determine the logic value. If the stored charge is equivalent to VDD or close to VDD, the binary value will be 1. If the equivalent charge is close to 0 or ground, binary logic value will be 0. In some case, it will have the connection. In some case, it will be floating. In the floating stage, the capacitor will be solely responsible for maintaining binary values at the desired level. So that's the biggest differentiating characteristics between static and dynamic circuit. It will have floating node situation. Output node will be floating in half of the cases, and where it is floating, the logic value will be determined by the charge or voltage across the load capacity. Since in the floating node, the capacitor will be holding the charge, which is a parasitic capacitance, and there are lots of leakage components present in any logic circuit. So if you leave a capacitor in floating state for a long time, leakage, noise, environmental effect may actually quickly diminish that circuit, discharge that circuit, that node, and destroy the binary value. So a dynamic circuit must be synchronized and recharged again and again after every clock period, so that the floating node value is refreshed. That's why a dynamic circuit operation must be synchronized by a clock signal of a maximum clock period length. If the clock period length is too long, then the floating node will have enough time to discharge itself through leakage and lose the binary value. So you have to refresh it frequently. So the clock cycle length must be short enough. Clock cycle length must be short enough means frequency should be high enough. So every dynamic circuit, to operate correctly, it needs a minimum clock frequency. First, it needs to be synchronized and operated by a synchronizing clock signal. Second, it must be operated by a minimum clock frequency. So, here we are introducing another definition of electrical circuit. Electrical circuit from operation point of view are of two types: synchronous circuit and asynchronous circuit. Synchronous circuit or synchronous logic circuit must be controlled by a clock signal. It is called synchronous circuit. If the circuit operates by itself, there is no synchronizing signal, it is not synchronized against any clock or reference signal, it is called asynchronous circuit. So dynamic circuit is by default a synchronous circuit because its operation must be clocked with a minimum. So So that's why, because it has to be synchronized, and the output value in a floating node must be refreshed and reinforced back to its desired value. Operation of dynamic circuit is divided into two phases. One phase is called pre-charge phase. The other phase is called evaluate phase. In the pre-charge phase, so let's say if you have a clock period of 10 picosecond, maybe 3 to 5 picosecond will be for pre-charge, 5 to 7 picosecond will be for evaluate. During the pre-charge time, you do not apply new input. Your only job is to refresh the value back to the value where it is at the beginning. And then you apply new input and evaluate the output with the set of new input. So, in a static circuit, you can apply input signal at any permutation combination at any sequence. And every time you will get the correct output. But in dynamic circuit, whenever you apply a set of input, evaluate the output. Then, before you apply second set of input, you have to pre-charge it back to its default value. Every dynamic circuit will have a default value. We will talk about it later. So every dynamic circuit will have a default value. Whenever you apply a set of input, evaluate or calculate the output, you wait for the circuit to be pre-charged or refreshed back to its default value before you apply next set of input. So the operation is synchronized, and every evaluation phase, evaluation means application of input and evaluation of the output. So every evaluation phase must be sandwiched in between pre-charge phases. So dynamic circuit operation is divided into two phases, pre-charge and evaluation, and it is synchronous operation. So these are some characteristic features difference with static circuit. Now let me introduce the basic design of an N-type dynamic circuit. So dynamic circuit can be of two types. Dynamic circuit can be of two types. In the I'm drawing side. There is an N-type, this is a P-type dynamic circuit. An N-type dynamic circuit is comprised of pull-down network and two clock transistors. The function of this clock is to implement synchronization, pre-charge and evaluation. In a P-type dynamic circuit, the pull-down network will be there and two clock transistors, same. The only difference is here it will be clock bar and clock. Here clock bar, here is clock. Here it is clock, that is clock bar. Sorry, both of them will be clock bar here. So, now let's look at this operation of this one, then this operation will be just opposite. So, a dynamic circuit in general can have either a pull-down network or a pull-up network. So you have to always remember, output is always above pull-down network, always below pull-up network. So here, between output and the ground, there is only one MOS transistor. Here, between output and the supply, there is only one PMOS transistor. So from previous lecture, if you know how to construct pull-down network and how to construct pull-up network for the any given logic function, you should be able to draw the circuit for N-type and P-type dynamic circuit implementation. That is question number 1 of the midterm. You will be given a logic function. First step, simplify it. Step 2, implement the CMOS version. Question number 3, implement the pass transistor logic, sorry, the ratioed logic, the pseudo NMOS, then N-type dynamic, then P-type dynamic. So there will be 5 branches. So question 1 is out. That will be the probably 1/3 of the whole exam. So just yeah. So the next class we are going to, that's what we will do. We are going to discuss at least 3 different examples. I will bring in a printed sheet. I will not derive everything here. I will show the first original expression and the simplest version of this expression, and then implement it from there. So now let's look at the operation. So this circuit operation is divided into 2 phases. First phase is pre-charge, second phase is evaluate. For N-type dynamic circuit, when clock is 0, is pre-charge phase. Remember that, memorize that. When clock is 0, it is in pre-charge phase. When clock is 1, it is in evaluation phase for N-type dynamic circuit. So in pre-charge phase, what we do? We pre-charge the output to its default value. So now let us see what should be the default value of an N-type dynamic circuit. When clock is 0, this NMOS clock will be off. So the pull-down network is disconnected from the ground. So at that point, there is no point in applying a new set of input because pull-down network is disconnected from the ground. So pull-down network, no matter what you apply, logically, if pull-down network is on, there has to be a connection from output to ground for a binary 0, high to low transaction. But if the clock is off, when clock is 0, pull-down network is disconnected, so we should not apply any input. It is useless. But when clock is 0, that PMOS is on, output is connected to VDD. So output will be charged, pre-charged to what? VDD, binary 1. So the default value of N-type dynamic circuit is 1. So we learned 3 information. For N-type dynamic circuit, when clock is 0, it is in pre-charge phase of operation. When clock is 1, it is in evaluation phase of operation, and the default value or the pre-charge value of N-type dynamic circuit is 1. So in the pre-charge phase, this clock is off, that clock is on, output is pre-charged to its default value of 1. Now, in the evaluation phase, when clock is 1, this clock is on, that clock is off. Now output is disconnected from the VDD, now output is floating. It got a pre-charge value of 1, now it is disconnected from supply, now it will maintain the default value of 1 across this load capacity. Now I apply, in the evaluation phase when clock is 1, I apply my input. Input, when I apply the input, there are 2 possibilities. For a given input, if the pull-down network is on, output will be connected to the ground because this is already on. So the whatever we pre-charged, it will be discharged to 0. Any input that turns on pull-down network should produce a 0. So logically I am getting the correct output. But what if, for the given input combination, the pull-down network is not on? Then output will not have a connection to ground. Output is already disconnected from the supply. So for any input combination, if pull-down network is off, output should be 1. And that 1 will be maintained in a floating state by this load capacitor. But if it stays in floating state for longer time, leakage and parasitic path will distort the value. That's why before we apply another new set of input, we have to pre-charge it again back to its default value. So in dynamic circuit, it's pre-charged, evaluation, pre-charge, evaluation. For n-type dynamic circuit, pre-charge is clock equal to 0, evaluation is clock equal to 1, and default value is 1. In p-type dynamic circuit, it will be exactly opposite. Clock is 1 means pre-charge, clock is 0 means evaluation. If clock, when clock is 1, this one will be on. We can actually implement it this way as well. When clock is 1, this one will be 1. Default value of the output will be 0. So for n-type dynamic, pre-charged or default value is 1. For p-type dynamic, pre-charged or default value will be 0. Here, clock 0 means pre-charge, clock 1 means evaluation. Here, clock 1 means pre-charge, clock 0 means evaluation. So, that's all we need to know. In the next class, we will look into. Yeah, what?
In today's class, the question was from this topic. Advantage and disadvantage of CMOS dynamic logic.
We had some discussion in the lecture 3 and 4 as we were talking about the classification. I must have overlooked